Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, almost we are concluding this topic, that is this module. We have seen what are the main effects of the radiation environment on the spacecraft, namely the total ionization dose, then displacement damage and the single event effects. So, in this session we will be discussing what are these different modeling and simulation techniques and how the testing can be done. Because for any the device or any material to use in spacecraft, we need to know what is the radiation properties, how much it is resilient to the radiation. So, in order to do that, we need to do the modeling and simulation as well as the testing. So, that we can characterize the material, whether the material will be able to withstand the radiation dose or not. So, once you do that, then there are this modeling and simulation testing itself, it is a part of the mitigation. Once you know all these things, then what are the mitigation towards the space radiation risks. So, we will discuss these two topics. So, first is the what is the modeling of the radiation environment. So, before we decide or when the spacecraft is being designed, at the time of design, the spacecraft designers, they used several radiation modeling codes to define the environment and to predict its effect. So, those codes will be able to simulate the space environment and then how it is affecting. So, this can be seen on the using the computer codes. So, why it is important? Because each spacecraft should have those some shielding or different the protective measures, like using the shielding. So, what is the the extent of shielding, what should be the metal thickness to be used, that will depend on what is the radiation dose. So, that will come from the prediction through modeling and also the mission planning. So, the radiation risk management for the astronauts' health, especially for long duration missions beyond low Earth orbit. So, this needs to be, so during the mission planning also you need to have an idea or need to have a simulated some prediction of how this radiation risks can happen to the material as well as to the health of the astronauts. Then the performance of the so overall the system, it depends on the reliability of the subsystems, all the payloads. So, whenever we have to consider the reliability of this the electronic subsystem. So, it is very much important to understand the radiation environment, which helps to design the radiation hardened components. So, these modeling codes, they contain models of the environment, as I already said, and those models can perform the radiation transport calculations, which are necessary to determine the dose versus shielding depth. We will now see what are the different types of the modeling available. So, the models for the space radiation environment. So, there are the empirical environment models. Empirical means it is based on there is some formula or some mathematical formula, which is those mathematical expressions are derived from some of the, it can be mainly it is the what is the data available. So, that is why it is called the empirical environment models. It is not based on the physics based model, but it is based on the already available data and the curve fitting over those data. So, those empirical environmental models, there are a few like AE8, AP8. So, I will say why it is AE and what it is AP. So, models of trapped electrons and protons. E means the electrons and P means in this AE8 means it is that is the trapped electrons, or Ap means the trapped protons. Then there is the other type, it is CREM E96 or CRME MC, that I will tell you what are the full form of these terms. So, these are the cosmic ray environment and the solar event models. Then there is that ESP, then SEP, EM. So, these are the empirical environmental models for the solar particle event models. And the physics based models, so here actually the simulation of the particle transport, considering the through magnetosphere and the solar wind interactions. So, here actually it is a physics based models, where actually you are considering the how the charged particles are transporting in the magnetosphere in the presence of the solar wind. Okay. Now, the orbit dependent radiation dose calculations. So, they use the spacecraft's trajectory to estimate flux and the spectrum of radiation over the mission duration. And now, what are the software tools? We will discuss more also, but here there is one is the shield dose, or it is space reg. This is a trademark. So, this is the computer codes for space shielding radiation dose calculations, and it determines the absorbed dose as a function of depth in aluminum shielding material of spacecraft, given the electron and proton fluences encountered in the orbit. Whenever this the fluxes of the electron and the protons, it should be known, then this tools, that is the shield dose, this can calculate what should be the depth of the, and what should be the thickness of the that is metallic shielding for the this hardening of the against the radiation. Then there is one more tool that is called the SPENVIS, that is ESA's tool for space environment modeling. Then one is OM array, this is CNES, multi environment space radiation modeling software. Then there is one more, that is NIRS for atmospheric ionizing radiation. Now, we will in short we will tell what are this the model. So, here the AE stands for atomic energy, commonly referred to as AE model. So, the AE8 model, it provides estimation of the flux of trapped electrons in Earth's inner and outer radiation belts as a function of position, energy and time. And it is usually it is used extensively in spacecraft design to predict the electron radiation exposure for satellites in Earth orbit. And the model is based on the data collected by satellites during the a lot of satellites during the 1960s and 1970s, and those satellites are mostly which are from the NOAA, that is the NOAA means the National Oceanic and Atmospheric Administration, and the other missions. So, as I said, since it is an empirical as a model, so you need the data so to build the model. So, there are two versions, one is AE8 max, max means it represents the condition at solar maximum, and AE8 minimum, min means the minimum, that is the solar minimum condition. And this model, that is the AE8 trapped electron model, it provides a global map of trapped electron fluxes, and electron fluxes of energies from 0.04 mega electron volt, that is equal to 40 kilo electron volt up to 7 mega electron volt, and it accounts for the geomagnetic field configuration using dipole approximations. Means this Earth's magnetic field is considered as a magnetic dipole, and it is widely used to estimate the radiation dose for planning the shielding, radiation dose due to the trapped radiation belt. Now, its counterpart is AP8 trapped proton radiation model. So, AP8 model, again P means the proton, so atomic proton, AP means atomic proton. So, this model, it estimates the flux of trapped protons in the Earth's radiation belt. So, it is used to predict the proton radiation exposure for spacecraft orbiting the earth, particularly for low earth orbit and medium earth orbit missions. So, as you know, that is this protons are predominantly present in the inner radiation belt. So, inner radiation belt it affects the spacecraft in the low earth orbits. So, that is why it is mostly used for the low earth orbit and medium earth orbit missions, and it has to be used together with the AE model, that is the electron model, for a complete radiation environment estimate. And the proton fluxes for energies, it ranges from approximately 0.1 mega electron volt to 400 mega electron volt. And proton fluxes it finds as a function of that is the magnetospheric radial distance. It is the same for the AE model. AE model also consider this what is the the magnetospheric the radius or the radial distance. Then what is the magnetic field strength, and what is the solar cycle phase, whether it is the solar maximum or solar minimum. So, it is same for the AE8 model also. Then the models for the galactic cosmic rays and the solar particle events or solar energetic particle models SEP. So, to predict the flux and the energy spectrum and the compositions of the galactic cosmic rays in space, which are usually the outside Earth's magnetosphere as a function of solar modulation level. I will just tell what is the solar modulation level, because the GCRs they are mainly it is influenced by the or it is modulated by the solar activity. This influences the galactic cosmic rays, because whenever there is the solar activity will have that interplanetary magnetic field. So, that interplanetary magnetic field it works like a shield. So, during solar maximum the GCR effects will be minimum, because it is shielded by those interplanetary magnetic field. So, that is why it is called the solar modulation. So, these are the typical models. So, one is Baudouin and O'Neill model. So, this is one of the widely used empirical models which describes the GCR fluxes as a function of solar activity. The next one is ISO 15390. This is a standardized GCR model for space mission design. Then this already I told in the in the previous slides. There is the model, it is called the CREME, that is cosmic ray effects on microelectrons. That is the full form, and there are the different models like CREME 96, then CRME 2009. So, these are the NASA developed models which combines the GCR as well as the solar energetic particle predictions. The other models is the tree. Tree means it is transient radiation effects on electronics. So, now as already I said, the solar modulation means during solar maximum the galactic cosmic rays flux decreases because of the enhanced solar wind magnetic field. This we also called IMF. Okay. So, now the next is solar energetic particle, or it is also called the solar particle event SPE. So, sometimes we call different name we are using, this is also called SPE. Both are the same. So, different books or different literature they uses different the acronyms. So, sometime it is called SEP or SPE. So, it is this models, that is SEP models used to estimate the probability and intensity, then the energy spectrum and the timing of the solar energetic particle events for mission planning and risk assessment. And this input, what are the input parameters? So, input parameters are solar event frequency, then what is the event size and the energy distribution and the time profiles. So, it is basically whenever this SEP is modeled, it has to be a function of the the solar cycle or the solar activity. So, depending on the solar activity, that SEP whatever the dose or this intensity, it will change as a function of the solar activity. That is why all these parameters are coming, the solar event frequency, event size, energy distribution and the time profiles. So, the typical models are ESP. So, ESP is emitted solar particle model. This is the empirical models, it predicting the probability and the severity of SEP events. Then the other model is JPL, that is JPL SEP model. So, this is based on the historic SEP event data. So, this is again it is an empirical model which is based on the what are the SEP event data available. Then there is one model available, that is called the King model. This gives it is a probability model for the SEP fluence. SEP fluence means the flux, SEP flux. And the variability, because already since it is a function of that is the solar activity, and solar activity is high, that there is a highly variability in the solar activity. So, this SEP will also be it is a very much variable, that is the events are highly sporadic and unpredictable, and with intensities it can vary several orders of magnitude. So, it is this SEP are also important, the space weather parameter. Now, you see these are all the that is the modeling techniques we discussed, that is you can have a model to predict different space environments depending on the data available using different models, but that may not be very robust. So, what is needed to in order to have or the increase the reliability, what is needed, that is you are to need to do the testing also, because the multitude of the phenomena that may arise from the interaction of the radiation with the matter, that is this, that is why the radiation testing of the devices as well as the materials is a very important aspect of validating a spacecraft design. So, the way the simulation is also important, testing is also very important, and when you validate your simulation, sometimes the simulation results are also validated through testing, and sometimes your simulation may not be accurate also. So, in that case, and testing also sometimes the test condition, it may not be possible to create the exact test conditions. So, so both testing as well as simulations are needed, so that you can qualify or you can validate a spacecraft design. So, the key parameters which are that is the electronic devices are tested. So, this includes total dose effects that already we have seen, then the offset threshold, and what is offset threshold. So, offset threshold means this single event that offset. So, what is that the material can withstand an energetic particle. So, that this is the offset of the this semiconductor device is not happen. So, you need to estimate through testing what is that threshold for the offset. Similarly, the latch up. So, already we discussed what is the single event latch up. So, all those effects will have a threshold. Threshold means above that threshold there can happen this latch up or those phenomena offset, or it can be burnout threshold, then it can be that neutron damage effects. So, all those effects, what is the threshold, what is the maximum this dose or maximum this thing can the material can withstand. So, that can be known through the testing. So, a variety of equipments are available for to carry out this tests, and we will just simply mention about that is the flash X-ray machines and gamma immersion sources. So, these are the the sources or the uses to simulate or to create a radiation environment by creating energetic particles, radiation particles. So, we will tell about the flash X-ray machines. So, these are often used to simulate transient ionizing radiation, and the device it consists of a the bank of charged capacitors, and the charged capacitors are used to they store electrical energy, and when these capacitors are simultaneously discharged, the energy is used to generate an electron beam through the process of field emission. Field emission means you are using very high electric field to excite the electrons from a a material, and then that will give rise to striking out of the free electrons from there. So, that is called the process of the field emission. So, those electron beam which you are getting from this field emission, this electron beam alone may be used as a radiation source, or a tantalum plate which is used for the generation of the X-rays. This can be used to convert the beam energy into Bremsstrahlung X-rays. So, doses of the order of 1 megarad, and silicon is used because we are using it for these it means it is not for the biological the dose. It can be obtained from the electron beam, or it can be 1 kilorad from the X-rays. So, when you are using the direct electron beam, you can get up to 1 megarad, and it can be this operational time of the order of it can be tens of nanoseconds. The dose and the dose rate, it can be varied by adjusting the distance between the source and the object which is being exposed to the radiation. Now, some concentrated sources of radioactive materials also can be used to subject samples to doses of either alpha, beta or gamma radiation, depending on the nature of the source itself. So, this is one method generating through that is the flash X-ray. So, other method it can be the cobalt 60 or cesium 137s. These are both gamma emitting sources that are often used in immersion studies, which is the other method we said, and single event effects may be simulated using californium. So, that is CF 252. So, having the atomic mass that is 252, that is 252 the atomic mass unit, and this emits the alpha particles. So, you see all these heavy the elements like cobalt, then cesium. So, these things are used for the this gamma ray immersion studies, that is that to expose those or to irradiate those material under test to this type of radiation. Now, we will discuss some design guidelines and the mitigation techniques. So, we will just see from this table, the table will come now. So, the designer has a variety of options to exercise to combat with the the radiation environment. So, in order to do this hardening, so there are two biggest mitigation techniques. One is the shielding and the other is the part selection. So, on the part level, the key is to radiation hardening is to select parts with sufficient tolerance for radiation. So, we will just see from this table. So, whenever the shielding, so what is shielding? So, it is to place structures between the sensitive electronics and the environment in order to minimize the dose and dose rate. So, this is using the metallic the metallic coating or metallic layer between the sensitive electronics and the environment. So, this is the shielding, then you can have this, this is the part selection. So, utilize the parts that have sufficient total dose safety factors and are latch up and upset resistant. Okay. The third is the redundancy. So, oversize the solar arrays, because the solar array will have its the natural degradation. So, that the solar arrays they perform also at the end of life. So, that is why the design guidelines is that you use oversized solar arrays and design electronic system with backup circuits and parts. So, this is the redundancy. In case of one is failures, there should be a redundant parts. Then there should be the recovery algorithms, the install the software capable of recovering the system from latch up or upsets. So, this should be available. Now, we said about the that is the the approved that is used the parts. So, those parts which you are selecting, they should have a safety factor of 5 or above. That those can be used with confidence, but if the safety factor is of the order of 2 to 5, it means it is if it is less than between 2 to 5, then it may be needed to carry out additional testing, or this that is the piece part traceability. Traceability means those elements should have a proper tracing, where it is used, what are the tests, what are the performance, at each stage it should be traceable. But if the parts safety factor is less than 2, so it should not be used. In some cases, if there is no other ways, then only it should be used, otherwise it should be avoided. For single event defect, the resistance of the single event effects, one should use the device having the LET threshold, which is greater than 100 mega electron volt per milligram per centimeter square. On system level, because certain failures or upsets are inevitable, the system must be capable of working around these events. So, always you cannot use something that it will satisfy all this or against all the environments. So, in that case it has to be capable of working, or there should be sufficient margin. So, the general fault tolerance techniques should be used for both the hardware and software when the mission is very critical. So, for this success of those mission, it has to be a fault tolerant technique should be used. So, with this I will end here, and this total module we discussed the different types of this, what are the effects can happen to either this material or the electronic devices, and then also we discussed about the effects on the this is humans, that is especially the astronauts. And here we will conclude this module, and the next module we will start with this is the reliability engineering. So, we have studied the different the radiation different space environments and its the risks. Now, how to evaluate the risks, what is the mathematical model, that we will discuss in the next module. We will start from the next session. Thank you very much.